All right, so the first two relations that we talked about yesterday was the reflexive property, I should say relations, properties of relations, the reflexive property and the irreflexive property. If you recall, the reflexive property was in a relation in its ordered pairs. This was when you had all of the ordered pairs that were doubled up. So the first and the second position were the same, and you had all of those guys according to your building set. If you had drawn your relation with respect to its digraph, with respect to its graphical representation, all of the little vertices would have loops on them. And if you were looking in the matrix down that main diagonal, you could have ones along the entire main diagonal. Okay? That was the recap on reflexive. Irreflexive was the extreme opposite of reflexive. This is somebody who's not just not reflexive, it's so far from being not reflexive. So here, very far from being reflexive. Sorry about that. So in terms of the relation, this is where it has exactly none of the ordered pairs where the first and the second position are same. So all of them are missing. In respect to the graphical representation or digraph representation, on each of your vertices, there's no loop. In other words, no loop in the entire picture. And if we look at the matrix representation, zeros along the entire diagonal, the diagonal of your matrix top to bottom here represents those ordered pairs of A, comma A, the zeros representing that they're not there. Okay? So that was reflexive and irreflexive. Now, in terms of the next three properties that we looked at to round out our 5 properties that we had, we also had the symmetric property. And a symmetric property said if you have, in terms of the ordered pairs, if you have an ordered pair in your matrix, reverse the order of your ordered pair, and you better have the other guy as well. Okay. Now, in this, notice the if. This doesn't say you have to have all ordered pairs. It just says if you have an ordered pair, then you have to have the reverse of that particular ordered pair. Now, just as an add-on to this, something to note about symmetric. We talked about it in brief a while back, but we talked about this particular relation. That relation with the little -1, anybody remember what it did? Well, it's the same symbol used for, if you remember back to some sort of algebra class where you did inverse functions, what happens, you had this whole thing where you had a formula like y equals 3x plus 4 or something along those lines, and you then swapped your x's and your y's and solve for where the new y was, or solve for x first and then replace the x's and y's. Both work just fine. But what it meant was that the role of the x and the y in your function swapped position. Well, it turns out that's exactly what it means in terms of the relation as well. So here, the r with a little -1 in what looks like an exponent position literally means you swap all your ordered pairs. Now, why would I put this next to symmetric? If, when you swap the order of all your ordered pairs, nothing changes, that means that you actually have both copies of each of your ordered pairs. In other words, both ways of writing the ordered pair, and that actually is another way of checking the criteria of is this relation symmetric or not. Now, asymmetric is you don't have that. So it says, hey, if you actually have one of the ordered pairs in your relation, you're not going to have the other one. And you don't have any of the doubled up ordered pairs. There are no A, comma A formatted ordered pairs. In terms of the digraph, if you have one connection between any two pairs, it has to be exactly one arrow. It's totally fine to have no edges, no connections between, but if you have one, it's only exactly one. In terms of the matrix, there were zeros along the diagonal. That's because you're not allowed to have these guys right here. You're not allowed to have the A, comma A ordered pairs. And in terms of the actual one arrow, if you have a 1 anywhere off this diagonal, in the corresponding position on the other side of the diagonal, it had to be turned into a 0. Fair note, if you have a 0 here, totally cool for it also to be a 0 down there. Now, antisymmetric was the last property we talked about last time, and that's almost the same as asymmetric. The only difference here is it's totally cool to have loops. So in terms of in the ordered pairs, it's fine if you have one or more ordered pairs. It's a format A, comma A. In the picture representation, totally cool to have one or more loops or no loops. And in the matrix representation, we don't care if there's ones or zeros along the diagonal. It doesn't matter. All we're looking for is if there's any ones off the diagonal in the corresponding position on the other side of the diagonal, it has to be a 0. Please note, if you're asymmetric, you're automatically anti-symmetric. You don't even have to check. If you're this one, automatically that one. All right, so that dealt with where we ended last time. And let me jump us to our definition of transitive, because this is our next property that we care about. So the next and last property that we're going to care about with respect to our relations is this property called this transitive property or transitivity. Okay, so the property of being transitive says you've got some relation. It's again on some building set. So given only one building set, that means your A is a subset of the cross product A cross A. Or if you prefer, R is all the ordered pairs of R. Both positions, the first and the second position, are coming from the set A. Okay. Now, here's a criteria for transitivity. If A is related to B, and then you also have that B is related to C, then automatically what that means is you better have that A is related to C. Now let's see what that actually means. In terms of the relation, so our ordered pairs, this means that if you have both the ordered pair AB and the ordered pair BC inside of your relation, then you better find A comma C inside your relation. And this has to work anytime you have a pair of ordered pairs like that. Okay? So what this says is you're checking all of your, for lack of a better word, length 2 paths. The length 2 is not an issue, it's the path thing. So it's totally fine if this is really a cycle. It's totally fine if this is really technically not a path or a cycle, as long as you have the 2 arrows involved in your digraph, or as long as you have the 2 relations and the ordered pairs involved in your relation. Now, what would this mean in terms of your digraph, since we just mentioned that? So in the picture representation, if you have a relationship between A and B and a relationship between A and C, so there's the length 2 path that I was talking about, then, and let me actually color code this. So let's get a different color real quick. Then you have to have the shortcut path, in other words, or the shortcut way of going. So instead of taking 2 arrows or length 2 path, you have to be able to get there in 1 step. Okay? So that's all it's saying in terms of the digraph. Now, in terms of the matrix, I'm not going to write out a matrix because the property is a little bit different. This is where you actually have the following property. So note, what does this mean? This means if you built your R2 relation that we did at the beginning of yesterday, then all of those ordered pairs in the R2 relation have to also be ordered pairs in the original relation. So that's actually, if you wanted a property, we could actually put that right up here. So just like what we did with symmetry. Now, what does that actually mean? What that actually means is, remember what's going on with R2. R2 is an ordered pair where we just had what? The first position of the ordered pair in R2 was where your length 2 path started, so right here like A. And the second position of your ordered pair was where your length 2 path ended, so over here like C. It didn't bother with what these middle guys were. You could have multiple paths and that's fine. R2 only tracked where you started and where you ended. Well, regular relation R with only 1 step also would say where you start and where you end, but that's with relation to just 1 arrow. So if R2 is completely a subset of regular old relation R, that means automatically all of these length 2 paths have an associated arrow with it. And notice it is totally okay if R2 is equal to R. That happens. It's also totally okay if R2 is a subset of R. Now, here's how to calculate transitivity fast. What you do is you calculate your matrix that's associated with the original relation, and then you square it. No lies, I totally would do this in a calculator, unless the relation is really, really tiny. And then what do? Then you compare this matrix that you squared from R, and you check to see if all of those little entries are actually inside the matrix associated with the original R. Now, what I'm going to do here is I'm going to put a sort of equals symbol. It actually has a special meaning. I'm just going to use it as sort of equals, which isn't a lie, but it's not exactly what it means. Now, why would I say sort of equals? Because we talked about last time, one of the things that you would do is if you squared your original matrix associated with the relation R, which we didn't say how to do, this is where we're going to talk about how to square the matrix. But you'd square the original matrix, that's your Boolean matrix, you'll get back a matrix that is not necessarily Boolean. Okay? In other words, you'll get back a matrix that maybe it has a 2 or a 3 in it. It doesn't only have 1s and 0s. Then converting it into the matrix associated with the relation R2, we'll take all those non-zero numbers, including the 2s or the 3s that aren't 1, and pulls them back to 2 or 3, pulls them back to 1. Okay? So this here says, hey, we're going to have all the information collected here, but to put it back as the official matrix, there's a slight adjustment you have to do. Then what we do is you check if every position with a 1 in that matrix associated with R2 also has a 1 in the same position in the original matrix. Please note, this is just a way to allow your calculator to help you with the matrix arithmetic to check this thing right here. Okay. So let's do a little bit of a hiatus to make sure that we're all comfortable with squaring a matrix and getting to then the Boolean matrix associated with R2, or the matrix that only has 1s and 0s associated with R2. And then we'll go and jump into looking at an example with a relationship that will check actually all 6 of the properties. Okay. So in terms of matrix multiplication, so matrix multiplication. And honestly, it's probably easiest to see this with an example. So let's go ahead and look at an example. And let me color code this just because we're going to have a fair amount of writing on this particular slide. So suppose you have an example like this. And I'm going to, on purpose, do matrices that look like different sizes and have all different numbers, not Boolean matrices. We'll jump to specifically what would happen in Boolean matrices after we're okay with matrix multiplication. And I know about half of you said that you've done matrix multiplication before, so this should look very similar. If you haven't done matrix multiplication before, this is totally for you guys. So maybe you have a matrix, and here's a really lazy matrix. 1, 2, 3, 4, 5, 6. Probably one of the lazier matrices you could ever have. Now here's the thing with matrix multiplication. When you are doing matrix multiplication, first of all, we're going to be dealing with 2 matrices. So you're looking at A times B. Okay? So right now we wrote down a matrix A. Now I'm going to write down a matrix B next to it. And this matrix B next to it is going to look as follows. I'm on purpose going to pick different numbers. So here maybe we have 0, maybe -1. I don't want to get too big a number, so maybe some of these numbers will repeat. So maybe a 2, maybe a +1, maybe a 3, maybe a -2. Okay, and I'm going to claim that those 2 matrices are 2 matrices that are compatible with each other, that you can actually multiply them out. What are we going to do in terms of the matrix multiplication? We're actually going to multiply a row times a column. Now, there is a technical term for that, and it's called a dot product. But if you haven't had enough math to get to a dot product yet, don't worry about it. I'm going to show you everything that you need. So here's the strategy of what you do. And let me get back to another color. So I'll put this strategy, we'll put it right down here below. So strategy. Wow, that was not the right color. Oh well, strategy. Okay. So what we're going to do is in the product matrix, so this one here. So this is, I'll actually give you the formal notation. So what this says is in the product, once we get all done, in the ith row and the jth column, what are we going to do? I can't spell column today. We are going to multiply the ith row from the first matrix A, and we're going to multiply it by the jth column of this second matrix B. So that's the idea of what we're going to do. Now, that being said, it's a little bit more complicated than that because this guy here is, and I'm going to give you the official word, so if you wanted to look it up more, you can. This is known as the dot product, which is typically the name you see first. It's also known as the inner product, if you want to be very technical with it. So let us see what you would actually do. So if you actually want to go ahead and do the multiplication here, you would take for the first position in the product matrix, first row and first column. Okay? Now, notice, no, get back to real writing. There we go. Okay, so notice what are we going to be trying to do here? We are going to be looking at the first position in the first row and the first column. So we're going to multiply the first row and the first matrix together with the first column in the second matrix. Okay? So when you multiply it together, this dot product version of a multiplication says, I've got this whole list of numbers I need to multiply together, but I need to have just one entry. So what do? You multiply the corresponding positions together, and then you're going to add all of those products. So let me write it out. So you'll have 1 times 0. So that would be first position in first row, first position in first column. Then you're going to have 2 times -1. So that's second position in the first row, second position in the first column. And lastly, you're going to have 3 times 2. And then you actually have to figure out what that number is. Okay? Now, in order to get the next entry in the top row of the product matrix, since we're still in the first row, we're still going to take this highlighted first row in our first matrix that was given. But now if we're in the second column or second position in our matrix, we're going to use the unhighlighted column in our second matrix here. So matrix column 2 and matrix 2. Okay? So now we'll do the same exact procedure except first row, second column. So here we'll have 1 times 1, first position in the first row, first position in the second column. Then we'll, what did I even touch? Just a second. There we are. All right. So we have the 1 times 1 in the second column here, first row there. Second position, we have 2 times 3. So we have 2 times 3. That's second position, first row, second position, second column. And then lastly, we'll have the third position in the highlighted row and the third position in the unhighlighted column. Now, why would I know to close off? Because there's no other columns left in this second matrix. So notice here we have 1 row and we have 2 columns. First row has 1, 2 positions. And then we do the same thing for the second row. For the second row, we'll take the second row of the first matrix. So right now we're looking at the unhighlighted row in the first matrix. So we'll have 4 times the first position of, and if we're looking in second row, first column, we'll have second row times first column. So first position in the second column is 4, times the first position in the first column is 0. So 0 times 4. Then we'll have 5 times -1. So second position in second row and first column. And lastly, we'll have 6 times 2, and that is last position in the second row, last position in the first column. Anybody have a guess for what we should do in this next guy, and that second row, second column? And while you guys are thinking about what that format should be for this second row, second column, I'm going to go ahead and add up all of those numbers together. Anybody have a guess? Ooh, there comes in a guess. All right, so let's check to see. So second row, second column, we'll look at the two unhighlighted rows and columns. So we'll have 4 times 1. We'll have 5 times 3. We'll have 6 times -2. So the guess that came in, perfect. We'll just write it down. So 4 times 1, 5 times 3, 6 times -2. Now, while you guys were typing, I went ahead and just added these guys together. So in this first position, first row, first column, we had 0 plus -2, so we're -2, plus 6, so that equaled 4. First row, second position, or second column, we've got 1 plus 6 plus -6. So the 6 and the -6 cancel to give us 1. And down here, second row, first column, was 0 plus -5 plus 12, and 12 minus 5 should be 7 unless I messed up the arithmetic. Now the one we just got was 4 plus 5 times 3, so 4 plus 15, and then minus 12. Well, 15 minus 12 is 3. 3 plus 4 looks like 7 again. Okay? So that would be the idea behind matrix multiplication. Notice what you have to have in terms of the sizing of the matrix. This only happens if your matrices are not square. You have to watch out that the number of columns in the first matrix, in other words, how many numbers are in your row, matches the number of rows in your second column or number of entries in your columns. Otherwise, when you try to multiply these together, you'll get one extra or more than one extra entry in either the row or the column, and that's when the product is undefined. Now for us, we're only going to look at the cases where we have square matrices where all the entries in the two matrices are 1s and 0s. So we don't have any of the extra things you have to worry about when you're actually dealing with random matrices that you're multiplying together. So let us now look at an example of this matrix multiplication specifically in our context. So in the next slide, I've got it basically blank, and we'll have an example of what happens if you're dealing with our type of matrix multiplication. Okay. So here, suppose you have the following, and let me go ahead and highlight this example in a different color. Apparently, it doesn't want me to do that. Okay. So for example here, suppose we have the original matrix, whatever it is. So let's do, I probably should do 3 by 3. So I'm just making up the numbers, 1s and 0s. So 1, 1, 0, 0, 1, 0, maybe 1, 0, 1. Okay. Now, in terms of what we're going to be doing, we're going to be dealing with just taking a single matrix and squaring it. Now, if you take a single matrix and squaring it, any guesses what that would mean in terms of the matrix multiplication? Don't overthink it. Well, matrix multiplication is always what? You're going to be multiplying more than one thing together. So when you square it, this is just the shorthand notation for having 2 copies of the exact same thing. Notice if you have a square matrix, in other words, a matrix that has the same number of rows and columns, they're going to be exactly the same size. And if you look at the number of elements in either a row or the number of elements in a column, it's always going to match exactly the same. So you're not going to have any issues where the product is undefined. And since they're exactly the same copy, if you reordered the order that you wrote your 2 matrices in, it will not matter. Okay? So let's see what would happen if we wanted to multiply these 2 matrices together. So it turns out we do the exact same thing as before. You're still going to go ahead and multiply your corresponding rows and columns together. Let's see if I can't get this to highlight. And apparently it's not deciding to highlight on me today. So if we want to actually multiply this guy out, if we look along the first row, we'll be looking along the first row in the first matrix, so the 1, 1, 0. And then to get the first row, first column, we'll multiply that guy along the first column. Okay? And we'll expand this out for maybe a little bit, and then we'll go a little bit faster. So when you multiply those guys together, what happens? So looking just at the row and column with the arrows, you multiply the corresponding position, so 1 times 1. Then we have in the second position 1 times 0. Then in the third position, we have 0 times 1. Now, when you multiply those guys together, notice what happens when your entries are only zeros and ones. Well, the 1 times the 1 will give you back a product of 1 in this first position right here. But the 1 times the 0 and the 0 times the 1, what happens with both of those two positions, or both of those two products? They're both going to turn into what, in other words? Don't overthink it. 0 times 1 is what? Yeah, it's just 0. So it turns out, because we're dealing with multiplying 1s and 0s together in a variety of combinations, because 0 times anything is still 0, the only way you're going to get back an actual number answer, I shouldn't say that, you're always going to have number answers. The only way that you're going to get back for each of these little small products, something that's not 0, is if you have 1 times 1, which makes it quicker to do the arithmetic. So for example, if we look at this second guy, so now first row, but second column, what happens? We'll have 1 times 1, which gives us 1. We'll have 1 times 1, which gives us another 1. And then lastly, we have 0 times 0, which will give us 0. You can actually do it even quicker, specifically counting up the matching ones. So if we do the next position, which is first row, third column, what happens? 1 times 0 is 0. 1 times 0 is still 0. And then 0 times 1 is still 0. Okay? And that takes care of the first row. Now, second row. If we look at the second row, first column, so we'll multiply the second row times the first column. We'll get 0 times 1. We'll get 1 times 0 and 0 times 1. Notice in each of these cases, we've got a 1 and a 0 being multiplied together. So this is the same thing as 0 plus 0 plus 0, or just 0. Now, second row, second column, still the second row, but now in the middle column right here, here we have 0 times 1, so that's 0. The middle position is 1 times 1, so that would be 1. And the last position is 0 times somebody, so that's going to be 0. 0 times 0. Now, second row, third position. Second row, third position, we have 0 times 0, so that's going to be 0. 1 times 0, that's going to be 0. And 0 times 1, that'll still be 0. Now, I'll let you guys figure out the last column. I should say last column, last row, excuse me. So what do you guys think would go here? And it's okay just to jump straight to the number. It's actually, once you see what's the pattern that's going on, jumping straight to the number is relatively straightforward. And we'll actually do that when we enter in those numbers up here in the matrix. So what do you guys think? What should we put in this last row, this row 3? In other words, row 3 times each of those columns. Now, quick check here. This matrix that we just got, okay, it's totally the square of what we wanted to do, of this original matrix. The original matrix up here was a Boolean matrix. And remember, a Boolean matrix just meant it had all 1s and 0s. What do you guys think? Is this matrix that we got, this product, this power of 2, if you will, of the original matrix, is that guy a Boolean matrix? What do you guys think? Hint, the answer is yes or no. Ooh, I've got guesses for both. Now, let's remember the definition of a Boolean matrix. So Boolean matrix means you only have zeros and ones. So do a quick check for the rest of you guys, since right now we're split 50-50. Is the thing a Boolean matrix? Ooh, we got to change. Anybody else have a guess? What do you guys think? Boolean matrix? So for those of you who think no, since those are the only guesses I'm getting in right now, what would be the giveaways that this guy is not Boolean? Because you're right, it is not a Boolean matrix. What's the giveaway? How did you know it was not Boolean? Yeah, it's totally because of those 2's in the matrix. Now, if the original matrix, if this guy right up here that we squared was actually corresponding to some relation, these ones would correspond to the individual ordered pairs in your relation. In the digraph, these guys would correspond specifically to the arrows in your digraph. Notice with ones down the diagonal here, it would be reflexive. Down here, what this would tell you is the 2's. This 2 right here would tell you that there are 2 ways to get from vertex, whatever vertex was on the first row, to whatever vertex was on the second row. So these guys totally model things that are important, but they wouldn't model things that's the actual matrix associated with R2. So if the matrix associated with the original relation R is this first guy, so 1, 1, 0, then 0, 1, 0, 1, 0, 1, then the matrix associated with R2 would be almost this square matrix. The only thing you do is change the 2's. The guys that make it not Boolean, you change them into 1's. So this guy would be 1, 1, 0, 0, 1, 0, and then 1, 1, 1. Okay. Now, this actually was not an original example that I had prepped up for us, but we could actually figure out if this particular, if the relation that goes with this particular matrix has the various properties. So if we looked at the various properties, first thing to know is you can read everything off of the matrix right here, but you can also, if you want to, put it into either ordered pairs or the graphical representation. Let me go ahead and do the graphical representation for us. So let's go ahead and assume that A is, let's just say 1, 2, 3. You'd have to know what your building set is. So if you have 1, 2, and 3, what does this matrix tell you? Top row would correspond to vertex 1. So this tells you in the first position that you have a loop at 1. Second position tells you that you have an arrow that goes from 1 to 2. Next one is on the second row. So second row says you're going to start at vertex 2. That little arrow says, or this little 1 says we're going to go from 2 to 2. I'm counting rows and columns here to get those numbers. And last row right here, so third row, first column says start at 3, go to 1. And the last one here says third row, third column, says start at 3, end at 3. Okay? So if you really like the picture, you can always convert your matrix into a picture. You can also always convert it into the ordered pairs by doing the exact same thing. Okay? Now, since we just talked about transitivity, what do you guys think? Is this relation transitive? What do you guys think? Is it transitive? And the answer would be no, and there's a couple different ways that you can see it. In the digraph, This guy is small enough that you can actually see it. Notice there's a length 2 path, 3 to 1 to 2, but there's no direct shortcut 3 to 2, which means it's not going to be transitive. So I can actually write that down. This is because we do have 3, 1 and 1, 2 in our relation, but 3, 2 is not in the relation. And as soon as you have one missing shortcut connector here, it's not going to be transitive. Now you can also see it in the graphs, which is why we were doing this whole aside that we've just been doing. Anybody spot what the issue is in the graphs? It's specifically, there's a 1 somewhere where it can't be if our relation was transitive. Ooh, not quite. So the question that came in said, does transitive mean that they all connect with each other? No, all transitive tells you is, and let me go back a slide to show you the picture. All transitive means is if you do have one of these where you've got 2 arrows stacked in a row, and I'm going to focus on the picture just because it's easy to see with the picture. You've got these 2 arrows stacked in a row, so what in this case what looks like a path, you always can jump there in one step. Transitivity essentially means you can link your relations. Think of like equal symbols. If 2 is equal to 2 is still equal to another 2, or maybe inequalities are better. 1 is less than 2 is still less than 3, well 1 is less than 3. That would be the type of thing. It just says that you can stack up the relationships. So in terms of the picture, you've got to check that all of these length 2 paths have the shortcuts, but not necessarily all the vertices themselves have to connect with each other. And I think I've got an example that will talk about what you're asking there in just a little bit. I think it's 2 examples in the future. Did not mean to go that far. So this guy turns out to not be transitive because we found one issue. If you looked in the graph, this graph that corresponds to R2, so all of your length 2 paths, you would need to have all of these 1s in their corresponding position in the original matrix. Notice first row is the same, so that's fine. Second row, we've got all of those 1s, we're good. But in the third row, we actually picked up an extra 1, and that extra 1 is actually the missing ordered pair right here that we would need. That's the missing arrow right here that we would need. So that's why these matrices are awesome, because this matrix calculation, while you can totally do it by hand, you can also plug this into a graphing calculator, have the calculator square it, and then just compare the matrices. Okay? So that is a shortcut way of dealing with transitivity. And I say that because transitivity can be a pain in the butt to actually see without doing some sort of work like this behind the scenes. Okay. We can also check the other properties. Maybe we go in order for the rest of them. What do you guys think? Is this relation, which we actually haven't written down, but we just have the matrix representation and the graphical representation of the relation, do we think the relation is reflexive? What do you guys think? Well, let's do them both together. You guys think it's reflexive or irreflexive? Both? Neither? I got a yes for reflexive, so yep, you're right. We got loops on all of the vertices, or in the matrix, we've got 1s down the diagonal. Both are the fast ways to check. What about irreflexive? What do you think in that situation? Irreflexive would be a no. So here, because we have these little loops, you're not going to be irreflexive because irreflexive said no loops or all zeros on the diagonal. What about the symmetry, asymmetry, or anti-symmetry? Do any of those apply? Turns out only one of them does. So which of the next 3 do you guys think would apply here? The symmetry, asymmetry, or anti-symmetry? And remember, symmetry says if you have one of your ordered pairs, you have the reverse of the ordered pair. Asymmetry said if you have an ordered pair in your relation, that's the only one, the reverse isn't there. And you can't have any of the doubled up ordered pairs. And anti-symmetry said if you have the doubled up ordered pairs, nobody cares. And if you have an ordered pair where the first and the second position are different, You're not allowed to have the reverse. And yes, I said that in terms of the relation, the one thing that we don't actually have listed out here. So any guesses? Symmetric, asymmetric, antisymmetric. Yep. It turns out antisymmetric is the one that we have. It's not symmetric because in terms of the picture, this arrow 1 to 2, we don't have the arrow going backwards from 2 to 1. In terms of the actual matrix over here, Rm, notice across the diagonal, they're not the same, which means it's not going to be symmetric. In terms of asymmetry, you've got loops, so you can't be asymmetric. So with symmetry, the issue here was the single arrow. With asymmetry, the issue here was the loop. Okay. And in terms of the antisymmetry, all of the arrows who are not loops, so in the picture, they are just single arrows. Okay. So this guy has exactly two properties, antisymmetric and reflexive. Okay. So that's the crash course in dealing with the matrices, and that's literally all the stuff that you need with matrices. I've got posted up on Canvas, and I can't remember if it's in this section or if it's not, I'll go and pull it into this section so it's easy to find after class. But I've got a section where I've got a bunch of stuff about different matrices all put together. One is actually a slideshow, and I don't know if that one is currently visible in Canvas, so I'll make that visible for you guys. And the other one is a PDF that gives you way more than you need for this semester or this summer session. All right. We're not going to be dealing with that one in terms of the echelon form or the reduced echelon form. It's not going to matter in this particular case. I know that it looks similar because Boolean matrices only have the zeros and ones, but that's not going to be a factor in anything that we're going to do with the matrix associated with the relations. Although I have to admit, I so often deal with those guys with their acronyms. When you actually wrote it out, it took me a second. I was like, wait a second. Yes, but he's being very proper. All right, so let us move on to an example, and I see several of you already found the example. Since it keeps flying up here. So for this guy right here, for this relation, went ahead and gave it out in terms of the ordered pairs. So we're looking on our building set 1 through 4, and our ordered pairs are 1, 1, 1, 2, 1, 3, 1, 4, 3, 1, 3, 2, 3, 3, 3, 4, and 4, 2. And what we want to know is which of the properties hold in this particular relation, okay? So I'm going to let you guys go and answer this and poll everywhere. You can see the URL up there at the top. It's the same one we've been using throughout this summer session. If you've got it on an app, it's there as well. In terms of what I'm about to do, I'm about to switch to the next slide where I've got this exact same relation thrown up. And what I'm going to do is I'm going to start writing it out in the two other forms. So the form that's the graph, as well as the form that is the matrix if I've got space. I think I've got space for both. And then we'll come back and see what you guys think. All right, so if we draw this out with its digraph, first we draw out the building set, so that's 1, 2, 3, and 4. Then we we transform all of the ordered pairs into arrows. So 1, 1 is a loop. 1, 2 is just an arrow. 1, 3, the arrow from 1 to 3. 1, 4, the arrow from 1 to 4. 3, 1, start at 3, go back to 1. 3, 2, start at 3, go to 2. 3, 3, there's a loop at 3. 3, 4, we start at 3, we go to 4. And 4, 2, we start at 4 and we go to 2. And with my luck, I'm going to have the next fly-in actually be that graph. Hopefully not. And then if we look at the matrix associated with this guy, I'll go ahead and put labels on the outside because that has a tendency to help people when you're first starting. First row is going to correspond to all the ordered pairs that start with a 1. So 1 actually goes to all of the other positions. For the top row would be all 1s. Second row, nobody actually starts at 2, so those guys would be all 0. Third row, we've actually 3 goes to everybody, so we'll have all 1s. And in the 4th row, 4 only goes to 2, so we'll have 1, 1. We'll have 3 zeros and 1, 1. And assuming I didn't screw up those numbers, that should be the answer there. Okay. So the question, of course, is, what do we think about this particular guy in terms of it being reflexive, irreflexive, symmetric, asymmetric, anti-symmetric, and transitive? And it looks like many of you guys have guesses, so let's see what happens so far. I can't find my cursor. There it is. So it looks like a lot of you guys think it's reflexive, and then it's all over the place for the other ones. Okay? So let us actually, I can't find my cursor. There it is. So let us now see if we think that's right. Okay? Oh, I've got more guesses. Excellent. I was trying to get it so you guys could see the graph at the same time and thought that it might help. Okay? So I will warn you, in terms of the guesses that are currently there, there's some issues. So let's see what we can do in terms of getting these answers. So if we wanted to talk about reflexive, lost my cursor again. Let's do reflexive and irreflexive together. Remember what the key thing with reflexive is. If you're looking in the ordered pairs, you're looking for all the doubled up ordered pairs. So we definitely have 1, 1. We definitely have 3, 3. Here's the question. Do we have the rest of the doubled up ordered pairs from our building set? Do we have 2, 2? Do we have 4, 4? Or some people find it far easier to go and look at picture. Remember what reflexive means? Reflexive means you have to have what? You have to have all your loops. So what do you think? Do we have all of our loops? We don't. So if you don't have all your loops, what does that tell you about the reflexive property? It tells you it's not going to be reflexive because you don't have all of your loops. So in this particular case, you could say, hey, it's not reflexive because we're missing our loop there at 2. Okay. Now, using that information, anybody remember what's going on with irreflexive? So I'm going to push you guys to the picture here because maybe that'll be easier to check. What do you think about irreflexive? What are we looking for in the picture for irreflexive? Remember, reflexive and irreflexive are totally dealing with what? They're totally dealing with whether you have loops in the digraph or not. So reflexive was you had to have all your loops. Irreflexive was you have to have what? Exactly, you had to have no loops. So what do you guys think? Do we have no loops? And hopefully you're all thinking to yourself, I see a loop. Maybe you see the 1 at 1, 1. Maybe you see the 1 at 3, 3. Doesn't matter which one you spot first. Just by the fact that you spotted some loops means it's not irreflexive. This is the most common thing to get with a relation, to have both not reflexive as well as not irreflexive. Now, it's not necessarily the most desirable case in any way, shape, or form, but if you just randomly grab some ordered pairs, that's typically what will happen. Now, moving on to the next guys. Symmetric, symmetric was the last one for this picture slide. So for symmetric Any guesses if this guy is going to be symmetric? And since we've got space, I'm going to go ahead and put all of the answers on here. So this one's not going to be symmetric. And what's the giveaway that it's not going to be symmetric? Well, the fact that you've got a single arrow right here. So here you've got the doubled up arrows, and that's fine, but you would have need to have all of these connections to be the doubled up arrows. So the fact that you just have a single 1 to 2, but you don't have 2 to 1, that means it's not going to be symmetric. Now, what do you think about asymmetric? Is it possible for this guy to be asymmetric? This one also not going to be asymmetric. And the giveaway with asymmetric, and this is the really, really fast giveaway with asymmetric, is look for the loops. If you have a loop, it's not going to be asymmetric, and you don't even have to look any further. So this one, the fact that we have a loop, so 1, 1, means it's not asymmetric. Now, if it's not asymmetric, it could still be antisymmetric because antisymmetric says loops. Sure, we'll take loops. But you do have to look for all your connections, and all the connections for asymmetric have to be single arrows. Well, that one is a single arrow, that one's 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 a single arrow. So are we antisymmetric? What do you guys think? We're really, really close to being antisymmetric, but it does turn out that we're not antisymmetric as well. And the issue here with the not being antisymmetric is between 1 and 3. Notice how we have both the connections between the vertices 1 and 3. This here, that looks like what you would want for symmetry. Because it's actually in this picture, you're not going to be the antisymmetry or antisymmetric. Okay? Now, we walked through all of these guys together. Those are the ones that we really focused on yesterday. There's only one guess here left. There's only one property here left to guess. And I've already given you guys the original ordered pairs, the picture, as well as the matrix here. So I'm going to give you guys a little bit of time. See if you can figure out whether this graph has actually one property. And the one property it might have would be the transitive property, okay? So I'm going to let you guys see if you can figure out. Once you get a guess, put it up on that poll everywhere. That way I know that you're done with having a guess. And I'll give you guys, let's say, a little bit of time, and then we'll get back together. That this thing is transitive, and it turns out that, yes, this guy does turn out to be transitive. It is the only property of these 6 that we've been talking about that this particular graph actually has. You can have a graph that isn't transitive as well, but in terms of this particular one, it does actually turn out to be transitive, and the easiest way to show this being transitive is to actually go and grab that matrix associated with R2, or just write out R2 like we did at the beginning of last class where we had the huge graph and all the little arrows, and check to see if, hey, all of those paths in R2 are actually a subset of the ordered pairs of R. Okay? So it turns out that that actually is true here for the transitivity. So let us look at another example. Oh, this was just... So suppose we have this next example here. And this next example, I also went ahead and pull it up and pull everywhere. That way you guys can have a chance to make a guess here. So this one is similar but a little bit different, and it looks like I'm accidentally covering up. I shouldn't say accidentally. There we go. So again, our building set is 1 through 4, and what we want to know for this relation, or I should say this relation, is the ordered pairs 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. And instead of writing it out exactly the same as before, I went ahead and just said, is this guy reflexive or irreflexive, symmetric, asymmetric, antisymmetric, or transitive? So while you guys are taking a guess, on the next slide I've got the same relation written out, and we'll look at what the digraph looks like, because I don't know about you guys, but I think it's easier to read this information from a picture. You can actually answer all of these questions straight off the ordered pairs. Personally, I find it easier with a picture. So here our building set is 1, 2, 3, and 4. We've got the ordered pair 1, 1, so that's a loop at 1. We've got the ordered pair 1, 2. Got the ordered pair 1, 3. The ordered pair 2, 1. The ordered pair 2, 2, so that's a loop at 2. Ordered pair 2, 3. Ordered pair 3, 1. Ordered pair 3, 2. And ordered pair 3, 3. And I'll go ahead and get the matrix here for us as well. The matrix associated with this guy off your building set, 1 through 4. 1 connects through 1 through 3. 2 connects 1 through 3. 3 connects 1 through 3. And there are no ordered pairs that include the 4. All right, so it looks like there are a lot of different guesses coming up, but based on the fact that you guys can make multiple guesses, it looks like probably about 3/4 of you have made a guess so far. So if it helps, definitely look at the picture and or the matrix to help you out with your guesses here. This is actually a really classic example. It is, however, more famous if one thing is removed from this one. So it's like very, very close to a classic example. All right, so I'll give you a little bit more time to take a guess for these guys, and then we'll see what the answers are. All right, I'm going to switch slides on you guys. Did everybody get the picture that you wanted to before I switched slides on us? All right, I don't see anybody yelling about it, so if you need the picture again, let me know and I'll come back to it. I'm throwing this up there in case you were having trouble finding the place. All right, the numbers have started to stabilize, so let's see what you guys have been thinking. All right, so you guys look like you've been thinking that, so not consistent for everybody, but there are definitely some clear winners here in terms of what you guys have been thinking. In terms of, and then some last minute changes, yes. Yeah. I want to make sure everybody has a chance. It looks like we're closer to everybody making a guess. All right, does anybody want any last minute guesses as I'm about to lock it? I may not actually lock it. All right, so you guys ready? You got all the guesses you wanted in? All right, I don't see any movement. So those are the correct answers. Okay. So let's see why, because it looked like, for the most part, you guys were agreeing that symmetric and transitive were pretty much the ones to go for. Let's see why some of the other ones weren't actually the ones to go for. Okay. So the main one that threw us, or threw many of us, was reflexive. Why is this graph or this relation actually not reflexive? Anybody spot why it's not reflexive? Why would this guy not be reflexive? Oh, that would work. In terms of not being reflexive, you don't have anything going on over here at 4. So this one here is the fact that we don't have that ordered pair 4, 4. In terms of the picture, no loop. In terms of the ordered pairs, no ordered pair 4, 4. Now, if we had crossed out 4, if 4 wasn't in the building set, so it wouldn't be in the digraph down here, it'd be crossed off. You wouldn't have a 4 by 4 matrix, you'd have a 3 by 3 matrix, so all those zeros would disappear. Then this guy would totally be reflexive. So watch out, this was sort of trying to be a trick question, specifically to watch out for your building set, because if you've got some of these extra elements in your building set that aren't used in your relation, that can really mess up your properties. Okay? It's one of the reasons why if somebody doesn't give you a building set, you assume that the building set is only the elements that are actually used in your ordered pair. Okay? So this guy turns out to not be reflexive because we have that stupid 4. Okay? Not irreflexive because you have all the other loops involved, or you have all the other doubled up ordered pairs involved. It is symmetric because all of your connections that you have are doubled up connections here. Now, it's not asymmetric or anti-symmetric for actually the same reason. Each of our connections right here are doubled up connections. So for both of these, you could say because you have like both the ordered pair 1, 1 and 3, 1. Now, the last thing was transitive, and it does turn out that this guy is transitive. There are some shortcut ways of finding that. One of them is looking in your matrix. If the ones in your matrix look like a rectangular shape, in this case it looks like a square, it turns out if you square the matrix to find that matrix associated with R2 that we've been working on before, the shape won't change. In other words, here we've put in as many possible connections, as many possible arrows as we possibly can, which means we automatically, if you've got all the arrows involved, you automatically have all of your length 2 paths have a shortcut of just a single arrow. Okay. So this guy is transitive right there. Questions? Make sense? Feeling a little bit more comfortable? Notice the only thing it looked like that through more than 1 or 2 of you was this 4. So watch out. Without the 4, this is totally an example of a reflexive, a relation that is reflexive as well. Okay. All right, so that's it for this example. Let us look at another example. I just had 2 pages for this one. All right, so this one is a little bit different. This one, instead of giving you guys ordered pairs, I gave you guys a picture graph, okay? So what do you guys think about this one? So it should be set up same exact way. You should be able to, let me actually cap that. Okay. Should be able to answer any of those guys in the, where are we? We're down here. Get that away. Can answer any of these guys that you want to. should be active right now. See if you think that this graph is reflexive, irreflexive, symmetric, asymmetric, antisymmetric, or transitive. Hopefully, the first 5 are relatively straightforward to grab, and the only one that we need to pay attention to is transitivity, just because transitivity is the one that's a little bit harder to check. Not always. I'll give you guys a little bit of time to make those guesses, and then we'll check. Or then we'll get back together. What's going on here with our answers? So looking at this one, it looks here that you guys think this guy has a clear winner of being anti-symmetric, and you guys are right. This is totally anti-symmetric. However, some of your other ones are not quite there. So let's, oh, and now things moved. Okay. So in terms of, any last guesses before I show you guys the answer? Oh, there's a couple last guesses. Any other last guesses? All right. Oh no, I can't find my cursor. So it turns out in this one, you guys are totally right in terms of anti-symmetric, but it turns out that it's also transitive. So let us see what's going on with the anti-symmetric and the transitive. Okay. So first of all, let's check in terms of reflexive. Notice here, reflexive, it's not going to be reflexive because you've got at least one of your vertices here that has no loop. It's not going to be irreflexive because you do have at least one vertex with a loop. So anytime you have this situation where one of your vertices has a loop and one of your vertices doesn't have a loop, you're going to be neither reflexive nor irreflexive, so both of those would be gone. Symmetric, you have to have the connections go both ways. So having even one arrow like this, that's a single arrow, means that's not going to be symmetric. Asymmetric here. Asymmetric means you can't have any loops. We have loops, so it can't be asymmetric. Antisymmetric has all the single connections and loops. We don't care one way or the other. So this guy is definitely antisymmetric. Okay, so that's the crash course in terms of why those guys work. So let us jump to the next slide where I can actually write on this thing. Okay, so reflexive, no, because of 2-2. Irreflexive, no, because of 1-1. You can use different loops or not loops. Symmetric, no, because 2-1 isn't in the relation, but 1-2 is in the relation. Asymmetric, no, because we have loops. And antisymmetric, yes, it is. Okay, so that's what we've talked about so far. Now, in terms of transitive, why would this guy be transitive? Okay, well, in terms of transitivity, you can actually look at this in a bunch of different ways. And remember, transitivity says if you've got A is related to B, B is related to C, then you have to find your A related to C. Well, if we actually track this, and this is one of the ways to find transitivity without doing the matrix. If we start at 1, we can go a lot of different places. We could stay at 1, we could go to 2, we could go to 3, or we could go to 5. Well, if we're at 1, we could still go to all those same places, so no worries. It turns out you don't normally worry about loops because loops will take care of themselves. Okay? Now, what you check is where you started, where you ended, is there one arrow? So since we used a loop, of course there's one arrow going from 1 to 2, from 1 to 3, and from 1 to 5. So that means we have all of those options. And that works so far. Now, if we look at 1 to 2, once we're at 2, we have to go to 3. So is there a shortcut directly from 1 to 3? And the answer is yes. Now, the answer of yes here is checking to see if that length 2 path is in the original relation. So this check mark says the length 2 path that we just found, yes, it's in this original relation as just a single arrow. If we start off and went to 3, where do you go next? If you go to 3, well, you can't go anywhere, so that's something we don't even have to check. Now, if we went 1 to 5, then we have to go to 3, and yes, we can directly go from 1 to 3, so that one works just fine. Now, if we started at 2, and this is where things get interesting. You start at 2, you have to go to 3. And if you go to 3, you can't go any further. So there's no length 2 path that starts at 2. If you start at 3, well, you can't go anywhere because there's no arrow leaving 3. So there's no length 2 path that starts at 3. So you don't have to worry about anybody there either. If you start at 4, 4 is going to be a mirror image of 1. So 4, you can go to 2, you can go to 3, you can go to 4, or you can go to 5. If you go to 2, you can then go to 3. And so then you check, hey, can I go directly from 4 to 3? And the answer is yes. So that one's in the original relation. That length 2 path is in the original relation. 4 directly to 3, where you can't go anywhere from 3. So that's not applicable. 4 to 4 uses the loop. So once you come back to 4, you can go to 2, 3, or 4, and 2, 3, 4, or 5, excuse me. Technically, we could have a 1 up here as well. So all of those guys are just using one arrow out, so all of those will be in the original relation R. And lastly, if we go 4 to 5, at 5 you have to go to 3, and we can get directly from 4 to 3. So all of those length 2 paths are as a single arrow in this graph. And if we start at 5, you can only go to 3, and you can't go anywhere from there. So all of the little guys that have an N/A or are not applicable on them are all the guys where you can't build a length 2 path. Okay? So that's dealing with transitivity brute force. Notice it's easier to deal with transitivity if the relation is actually transitive if you're dealing in the matrix, which is why we had that whole big aside about dealing with the matrix earlier. But this is the alternative way to dealing with the matrix. Okay. Makes sense? Kind of okay so far. Kind of is the key question there. Could at least follow it if I did it. Seeing no responses from you guys, I'm going to assume that means yes. If the answer is really no, shout out and we can talk more about this. All right. So that's it in terms of the properties that I'm planning on talking about. The next little section that we're going to go over is different types of relations, and the big one that we're going to look at is equivalence relations. Next week we're going to talk about partial orders, but I'll go ahead and give you the definition right now. Okay. So an equivalence relation is just a relation that has to be reflexive, symmetric, and transitive. Totally fine if it has some of the other 6 properties too, but you have to be reflexive, symmetric, or transitive. Okay. Now, a partial order is a relation that is reflexive, anti-symmetric, and transitive. So this one here, again, it's just a relation that has to have these 3 properties. Again, it can have more than those 3 properties, but it has to have at least these 3 properties. So we're going to focus on for the rest of today, and depending if we get to everything, I'm going to say probably no. The first 10 minutes or so of Monday's class, we'll focus in on some of the things that you can do specifically here with equivalence relations. Now, the first thing is just identifying if somebody is an equivalence relation. So here's an example. This is actually the exact same example that we had just a second ago up on the poll everywhere thing. And this one here, the only difference is we now don't have a 4. So this is the one that looks like this. 1, 2, 3. It had loops on all the cases. And the arrows went in both directions. And what we found previously was that this guy was symmetric, that it was transitive, that it was not anti-symmetric, and when we did it previously, there was an extra building element of a 4, which made it not reflexive. But here, now that our building set is only the numbers 1, 2, and 3, are we reflexive now? What do you guys think? Yeah, now we're actually reflexive because we have all of those loops. So this guy here is totally an example of somebody who is an equivalence relation. equivalence relation. And that's why I said the last example was pretty famous, because this is one of these smaller equivalence relations that we see. I know it doesn't feel smaller, but in terms of the number of vertices that we have, the number of building elements we have here, that's relatively small. Remember symmetric here in terms of the graph means you have your two-way connections anytime you have an actual connection. And anti-symmetric means you have exactly one arrow anytime you have a connection. Okay? Note, in both of these cases, it's totally fine if there are no arrows whatsoever between the two vertices. This here is very much the picture representation of those definitions. And I'll go ahead and give you this one as well. Not the formal definitions. One of the things I would definitely recommend is get yourself something centralized that has a list of what reflexive, symmetric, anti-symmetric, transitive, irreflexive, and asymmetric are. And I would recommend putting the formal definitions down there, as well as what do you need to spot inside the picture? What do you need to spot inside the matrix, depending on what you're actually given. Okay? So that would be the idea in terms of, in these guys, what's often you'll see, and I actually put together a quiz for you guys, I think it's due Monday, that deals with one of these guys, and what it has is it says, hey, identify the properties, and then the follow-up question is it an equivalence relation? And you say yep or no based off of your properties. Asymmetric is the same as anti-symmetric, except you also have no loops. So that would be the extra one. And this one is not bad either. All right, so that would be identifying equivalence relations. Now you can do all sorts of things with equivalence relations. And one of the key things that you do with equivalence relations is look at something called equivalence classes. And it's a way to break down your building set. It's a way to partition your building set. In other words, cut your building set up into pieces. So we'll get the definition of this time, and then it looks like next time we'll see an example of what this means. Okay? So at the start of Monday, we'll go back over all of our definitions of our properties and equivalence relations. We'll go back over this definition, then we'll have the example. So an equivalence class of some element, and this element comes from your building set. Okay? So right here. I guess I didn't need to write it in there. Symbolically, it has these square brackets around it, and it's the set of all the elements that A is related to. So in terms of the ordered pairs, you're literally pulling all of the elements from A that are in the second position of an ordered pair, where your first position of your ordered pair is whatever the element is that you're focused on. So that's the big thing that we're going to be building. Notice this is very, very similar to when we were talking about ranges back on day one when we were dealing with relations. And it turns out it is exactly the same thing. They're just called something slightly different for equivalence classes. Now, there's also something called the quotient set. And the quotient set symbolically is A and this slash and R. No, it's not a fraction, and it's actually read A mod R. It's weird in terms of the symbols. I know it actually does make sense mathematically, but in terms of what we're going to see in this course, you have no context for that background. This guy here is simply the set of all the equivalence classes of A. So bare minimum, what do? You throw all the elements from your building set into little square brackets, and bam, that's your set of all the equivalence classes of A. The only snag there is, remember when you're dealing with sets, this is a set. You don't do duplicates. So you have to watch out to see if any of your equivalence classes are actually duplicated. And the answer is yes, they are typically. So this is in general, but then if you actually wrote all of these out, you cross off the duplicated ones. And we'll see how to do that next time. And the last thing is the cardinality of your quotient set. This is the thing that people typically want, which is the number of the distinct, i.e. different, equivalence classes of A. So next time we'll start with an example, and it's really about the only example that we've got left dealing with the current topic that we're in, which is specifically looking at how do we build these equivalence classes and how do we use them to find the distinct number of equivalence classes or the number of different equivalence classes of your building set. Okay, so that's the crash course in terms of relations and equivalence relations. We'll get in and start using these things next week. Okay, but that is it for today. I will hang around for a few minutes if you guys have any extra questions or follow-ups, but we're done. There is no more for today.